Well, good afternoon. It is Monday, November the 30th. We're on a chilly, rainy day here at Spain Park High School, but we're glad to be inside exercising our brain, dealing with gas laws, okay? So, we are not going to be distracted today. We're going to be focused today. And we're going to concentrate. Now, I just had you guys read about real gases versus ideal gases. So I ask again, what is an ideal gas? Go ahead, Uzma.
Hold up. It's like made up of unreal molecules. It's an unreal gas whose molecules don't take up space because they're so small.
Okay. It's an imaginary gas, an unreal. There's no real such thing as an ideal gas. There are two assumptions made about it. Number one, that the molecules are so small that they're like a point on a line segment, infinitely small, so the size of the molecule is not a factor. Until when? High pressure, because what happens to a gas when you push it together? It can't, Boyle's law says that if you put infinite pressure, the volume ought to go to zero. But what happens to a real gas when you push them closer and closer and closer together? They turn into a liquid. Okay? So they're going to deviate from ideal behavior under high pressure. And then, Usman, what was the second thing that ideal gases assumption about an ideal gas?
They have elastic collisions.
They have elastic collisions, and what about their attractive forces?
They're negligible.
There are no attractive forces. Now, when you talk about gases, they're covalent molecular substances, so we're going to be dealing with IMFs. Are IMFs strong or weak? Weak. And they only operate over short distances. So in other words, the molecules have to be really close together in order for them to interact with one another. So as long as, again, as the gas molecules are spread apart, they still have the same amount of attractive forces. It's just they're insignificant because they're not close enough for them to matter. Now they come and they bounce off real fast, but they're going fast enough to where those attractive forces are not strong enough to have much of an influence at all. Now we know that real gases do have attractive forces, as weak as they are. Again, ideally, you could take, according to Gay-Lussac's law, that's volume, no, that's pressure and temperature. Volume and temperature is Charles' law, okay? That if you decrease the temperature down to absolute zero, what should happen to the volume? It goes to zero as well, right? Directly proportional. But we know that that doesn't happen, because what happens when you slow molecules down? Well, first off, how do you slow them down? Decrease the temperature. Okay? So as you decrease the temperature, you slow the molecules down, eventually what happens? Before that, the gas doesn't turn into a solid, it turns into a, what's in between a gas and a solid?
Liquid.
Oh, liquid, very good. Okay, we're getting our brains back engaged here. Okay? So it's going to turn into a liquid. Those attractive forces. Now I kind of think of it like having Elmer's glue on your hands. If I have Elmer's glue on my hands, as long as there's any motion at all, that glue is not going to make my hands stick together. Because it's so weak. Okay? On the other hand, if I take super glue and put it on my hands, well, I got to keep my hands moving pretty fast, otherwise they're going to stick together. Right? So depending upon the strength of that attractive force, it depends on how slow you have to move the molecules before they'll start sticking together. The stronger the attractive forces, the sooner they're going to stick together, the more they're going to deviate from ideal behavior. So what were the two conditions then you think were real gases are going to deviate, go away from ideal behavior? In other words, go away from Boyle's law, Charles' law, Gay-Lussac's law. What conditions?
High pressure and low temperature.
High pressure and low temperature. Because at those conditions, what happens to a gas? turns into a liquid, and liquids do not behave the gas, don't follow the gas laws. So they deviate from ideal behavior. So whenever a question is asking about which one's going to deviate the most of the time you're going to be dealing with the strength of the attractive force. You're going to look which one's got the strongest IMFs. They're the ones that are going to deviate the most at any given temperature. So why do we study the ideal gas laws and Boyle's law and Charles' law and all that stuff? Because under normal conditions of high temperature and low pressure, which we're at right now, the gases do behave nearly ideally. So the laws work until you get close to its condensation temperature, which is the same as the boiling point. The closer the gas is to being a liquid, the less ideally it's going to behave. That's something worthy of writing down. You guys are zoned out. You guys are not ready to be back yet. Okay? The closer a gas is to becoming a liquid, the less ideally it will behave. Alright, so hold those thoughts. We're going to look at some questions at the end of today that might deal with some of that. Okay? And I just posted an assignment, 5 pages, about 5 or 6 different practice AP questions more that will be due by Sunday. That's what you kind of work on when you're at home. Work on those, and then we'll kind of go over them when you come back and when we see each other. Alright, but these are the ones that you had to do for over e-learning and over the break. Okay? So, you got 5 liters of air. I think this was the second one, wasn't it? Or it's one of the two that you had to do. The volume of a sample of air in a cylinder with a movable piston is 5 liters at a pressure of P1. The volume is increased to 10 liters as the temperature is held constant. The pressure in the cylinder is now P2. What effect do volume and pressure changes have on the average kinetic energy of the molecules in the sample? Now, how many of y'all think the answer to this one is A? Does anybody think it's B? Does anybody think it's C? Oh, y'all are looking around. Okay? Hampton, why C?
Because kinetic energy never changes.
Because, well, kinetic energy does change, but what does it change with? Temperature. Temperature is a measure of the average kinetic energy. Since the temperature, here's the key right here, is the temperature is held constant. That tells us right there, average kinetic energy is going to be the same. So the reaction between SO2 and O2 to produce SO3 in a rigid reaction vessel is represented in the diagram below. Okay, so you're always going to have to look at these diagrams. Okay, what happens to the pressure as the reaction goes to completion? Now, first off, I want to point out, notice it says in a rigid reaction vessel. What does that mean, a rigid reaction vessel? What's constant? Volume, right? So when we change, okay, what happens to the pressure as the reaction goes to completion? Okay, when you have a constant volume, then the pressure can change. Okay, because you have more or less, the molecules either going faster or slower, you have more molecules, you have fewer molecules, the container stays the same size. If we have a flexible container, like a balloon, the volume is changing, but the pressure stays constant. So we need to always have that in our back of our mind. when you read this, since it says in a rigid vessel, that means that the volume is constant, but the pressure is going to change. So this question is asking about pressure. If it said a flexible container, that's going to mean that it's going to be able to expand or contract, and that's going to keep the pressure inside and outside the same, so the pressure remains constant. So if we cool it down, the volume gets smaller, but it's going to go down until the pressure gets back to where it was before. Okay? So, again, having a rigid container, a constant volume, the pressure can change. When you have a flexible container, the volume changes, the pressure remains constant. So this is telling me that okay, the pressure is going to change. So what causes pressure? Collisions,
On
what?
the surface of the container.
What's colliding with the surface of the container? The gas molecules. It's collisions of the gas molecules with the container wall. Right? What happens if you have more collisions? Pressure goes up. So you just count right here. 1, 2, 3, 4, 5, 6, 7, 8, 9 particles here. How many particles do we have over here? 6. So what happens to the pressure? It goes down. Okay? How much will it go down? Who you guys playing at?
Madison Academy.
Madison, are they good?
Yeah, they're pretty good.
But you're gonna beat them. You're gonna beat them, right? How much is it gonna go down by?
2/3.
It's gonna be 2/3 of what it was originally, or it's going down by 1/3. Because we have 6 particles versus 9. Pressure and molecules are directly proportional. So what's the answer to this one?
B.
Okay? Will the product molecules have a lower average speed? C.
Yeah. Wait, yeah.
Okay? So it's saying here, you got in 96, so we just said the pressure is going to decrease. We're saying the answer is B, because there's fewer molecules, but I want to know, will the pressure decrease if you have a low, the pressure will decrease because the product molecules have a lower average speed than the reactant. So when they spread out, do they slow down? Hampton, you're shaking your head no. Why?
I don't know, I just don't think so.
What, we just said in the last one, what average kinetic energy?
Temperature is constant.
Yeah.
So that it says right there the temperature is constant, so there's no speed change.
That's right. Temperature remains constant, therefore the average kinetic energy remains constant. It's the same gas, they're all going to be going the same speed. Okay? All right. We good with that? So now let's look at, forgot to pull this up. Practice questions you have to do. Classroom is blocked. Now, anybody bet me a nickel that you got all of these problems right?
I'm not a betting man, so.
You're not a betting man. I'm not saying you will bet me a nickel. How many you would bet me a nickel? No? No confidence you got them all right? Usman, you got confidence you got them all right?
Maybe.
Not a nickel's worth? All right. So let's look at it. So we have N2O4. What does the double arrow mean?
It goes both ways.
It goes both ways. So what state do we say that's in?
Equilibrium.
Equilibrium. Okay? So here's my starting. So in order to have equilibrium, and we're going to study this is when we come back, this will be like February, we're going to get into equilibrium full, and everything else we do all the rest of the year will be all about equilibrium. Okay? But equilibrium, what's equal in equilibrium?
The amount of each.
That's what we think. That's the natural thought, is that the amounts are going to be
The
equal.
rate of the reaction.
The rate of the reaction is what's equal, okay? The forward rate equals the reverse rate. So does that mean all of this goes to there? Only some of it, right? So it says a 4.10 gram sample, 4.10 gram sample of dinitrogen tetroxide is added to a previously evacuated 500 milliliter container of 273. Container is then heated to 400, causing some, not all, some, that's key, of the N2O4 to decompose into NO2 according to the equation above. Once equilibrium is established, the total pressure of N2O4 and 2NO2 at equilibrium is found to be 4.69. This is another key phrase in here, and I don't know if you printed this out or whatever, but if you could highlight that statement right there, the total pressure is, that's a clue as to how you're going to have to solve these problems. Okay? Now, A, if no decomposition occurred, in other words, it's all staying here, because this is the only thing that got put into the flask. Then it was heated and forced to go here. But they're saying you heat it up to 400, but just before it starts to decompose. Nothing's decomposed yet. If no decomposition occurred, what would be the pressure of the N2O4 in the container at 400? How do we find that?
PV.
PV equals nRT, right? So PV equals nRT over V. What does N stand for? Moles. How do I find moles from this?
Grams divided by molar mass.
Grams over molar mass. We don't even have to do stoichiometry, just molar mass. And the molar mass, we figured out 16 times 4 is 64, plus 14 times 2 is 28, so 64 and 28 is 92. I get 92.02. You want to carry it out a little farther? Times R, which is always 0.0821, times the temperature of 400 K, divided by the volume. What units does volume have to be in?
Liters.
So how many liters?
0.5.
0.5 liters. And all that turns out then to equal
3.
2.93.
Oh, well, I just saw that it said like 400 into 500 milliliters. So I thought that was like one safe thing.
Oh,
That's 400 and
I
500.
got you. Well, technically that is just one. There should be a decimal point there, and there should be a decimal point there. So let's just assume 3. You would be absolutely correct with 1/6. Just to move this up a hair. Oh. Okay, you guys can take a break, and when you come back, we'll look at some more of these. just for the record, I'm leaving the camera on, so, be careful what you say.
Yeah, I saw it earlier. I saw an article. Apparently, it's supposed to get to the 20s tonight,
Yep.
and which means it's also a decent chance of snow. At least snow flurries.
Florida.
Yeah, flurries.
Florida, that's what it is. No school cancellation, however, I would still watch the news to make sure, because.
There could be a chance, yeah. Small chance, but a chance nonetheless. Only 5 for us? Man. Or we might get sleet or just some gross snow. That's when we're talking about Huntsville. Huntsville's got a better chance of getting a rain snow mix. Regardless, it's cold and I didn't bring a jacket. I'm wearing long sleeves, so still, it's only a consolation at this point.
Well, I'll never wear long sleeves still inside. Okay.
Hopefully.
See, look, because he said it out nonstop. Alright. I don't know where she ended up at, but now, I'm going through, this is a multiple choice from a 2013 test, way back when, okay? So when I look at this, it says, the graph above shows speed distribution of molecules in a sample of a gas at a certain temperature. Which of the following graphs shows the speed distribution of the same molecules at a lower temperature as a dashed curve? Don't say the answer out. Which one shows the distribution of the same molecules at a lower temperature? What'd you think, Ken?
B,
B. Why B?
because it looks like it's got the same, like, starting and equal, so number, oh, wait, looking at, it was right along, never mind.
What'd you,
I was thinking, I can mix up speed and number of molecules on the
okay,
graph. So C, since it has the same peak, so the same number of molecules,
okay,
and but different length, difference, so a bigger speed.
okay, so that's close. But what happens to the range as it gets hotter and hotter? What does the range mean on a graph? You don't know? You didn't learn that in math? I know you learned it in math. What's the, just what do you think it's gonna mean on the range?
Wait, what do you mean? Oh, like this question.
On these graphs, what's the range?
Number of molecules?
No?
I don't think.
It's gonna be this distance, okay? The range always increases as you increase the temperature. In other words, you're gonna have some slow ones, but you're gonna have more that are fast ones, and so as a result, the average is gonna move to the right, but it's gonna be more spread out. So the hump always gets smaller. So what's this a graph of? Higher temperature. This is what it would look like if the dashed line is a higher temperature than the lower. So reverse that now, it says we want a lower temperature. Which one shows the lower temperature?
D.
D. Okay? Because this is your lower temperature, the higher temperature, it spreads out more, so it always gets lower, because again, the total area under the curve has to be the same. So if the range gets bigger, the peak has to get lower to keep the area the same. Because the area is the total number of molecules. Okay? Alright, scroll down, Mr. Sluss, one page at a time. There's some more in here that I want to see. Keep going. Alright, just out of curiosity on this one, this is a mass spectrometer. What does a mass spectrometer measure?
The mass.
That's a deep, right? Mass.
Crazy.
So, I'm not even going to read this question here, I'm just going to look at my answers. Te forms ions with a -2 charge, and whereas I forms -1 charge. Is that what the mass spectrometer tells us?
No.
Because the mass spectrometer measures
Mass.
not oxidation. That is totally 100% true. But that's not what we get from the mass spectrometer, because the mass spectrometer measures mass. Okay? Now, Te is more abundant. I consists of only one naturally occurring isotope with 74 neutrons. Okay, so those two deal with mass and abundance and things. We're coming down here, iodine has a higher first ionization energy. That very well might be true, but does a mass spectrometer do anything with ionization energy?
No.
So I can eliminate A and D right off the bat, now I'm down to a 50-50 chance. Okay? Now, I don't want to go through the explanation of this, I just saw mass spectrometer on there, so just, again, just highlighting that a mass spectrometer measures mass. That's something that we have to go over a lot because it's deep. Okay? Next page. Next page. Okay, so make this one bigger. Alright, so this is which diagram shows water vapor from hydrogen gas and oxygen gas. Make it bigger again, one more. Okay? Now what do we know about hydrogen gas and oxygen gas? What state are they in the normal pure form?
Yeah.
Gas, but what about, you know, what's unique about those gases? They're diatomic. What does that mean, Isma?
It's like when it bonds to itself. Or like-
It's bonded to itself, right? So it's gonna, diatomic, and how many are gonna be in a diatomic molecule? 2. So it's gonna be O2 and H2, right? So what's wrong with A and B?
They're not monatomic.
These are not these are monatomic, not diatomic. So we can immediately, not even have to count, do anything, eliminate these, because we know hydrogen and oxygen are diatomic. Okay? Now, when you look at these then, now you have your oxygens here. Which one of these is correct ratio?
C.
C.
There's 6
Right.
oxygens in both.
Because we have 1, 2, 3, 4, 5, 6 hydrogens to 3 oxygens of 2 to 1. What's the problem down here?
There's too many oxygens.
There's too many oxygens. Now, it would still react, but what should show up over here?
Extra hydrogen, extra oxygens.
The 3 extra oxygens need to be excess reactant over here. Okay? So, again, particulate diagrams of gases, knowing our diatomic molecules is very important. Okay? Next page. Next page. Next page. Okay. There we go. So we have 3 gases, methane, ethane, and butane. Okay? Here's their molar masses, 16, 30, and 58. Temperature is all 27, 27, 27, and the pressure is 2, 4, and 2. Okay? So the average kinetic energy of the gas molecules is
Same.
the same in all 3 containers. Why?
The temperature is the same.
Same temperature. Okay, see how that gets asked a lot? Okay? It's an important concept. Now, which one of those would be going fastest? They're all at the same temperature, same average kinetic energy, but which one would be going fastest?
Methane.
The methane, why?
It's the smallest.
It's the smallest. And the butane is going to be going the slowest. But they have the same average kinetic energy. So speed's not the same of gases at the same temperature, but the kinetic energy is. All right, the density. What is density?
How much of it there is per
Massive
volume.
Mass and volume, right? So we have to say they're all in the same size container, so the volume is all the same. So which one's going to have the greatest mass?
Butane.
It looks like butane because it's got the greatest molar mass.
But ethane has the greater pressure.
But ethane has double the pressure. What does that mean about the number of molecules?
Double.
It's going to be double, right?
Tricky.
So therefore, since this is double, what does that mean about the, let's just say that we had 1 mole of this and 1 mole of this, 58 grams in the liter, 16 grams, how much of this is going to be in there? 60. So that's going to have your greatest density. Okay? Now, if the pressure of each gas is increased at constant temperature until condensation occurs, which gas will condense at the lowest pressure? So in other words, you start putting pressure on it. So you're going to be increasing the pressure. Which one's going to condense first at the lowest pressure?
Butane.
Okay, why, Hampton?
Because it's bigger, so it's going to be stronger intermolecular.
Specifically, which one?
LDL.
LDS, right? LDS. Okay, they're all non-polar hydrocarbons, so the only IMF are LDFs, which vary with
Size,
of
electron.
the electron cloud, which we can use the molar mass to kind of help us with that. Okay, but it's the size of the electron cloud. And so, therefore, this has got the strongest LDFs, therefore it's going to stick together and become a liquid the soonest. It's going to deviate the most from ideal behavior. It's a biggest molecule, and it's got the strongest attractive forces. All right, next page. Next page. We'll go back to that one. This should look familiar from a test you just took. A problem just like that.
Really?
Next page. Whoa, go back that one. Let's look at number 26. Okay, I'm getting to the problem that I want to get to. Oh, which we haven't even done part B on this one, which is what I'm trying to work my way to. So we're going to take a break and let's do this one here. The figure above represents 3 sealed 1-liter vessels, each containing a different inert gas. What does the word inert mean?
Non-reactive.
Non-reactive. Okay? But we also call that the noble gases, or sometimes called the inert gases. The pressure of argon in the first vessel is 2 atmospheres. So if this is 2 atmospheres, what's this one going to be? 1 atmosphere, because pressure and moles are directly proportional. And this one's going to be
6.
6, and because it tells us it's 2 to 1 to 6 ratio without even having to count. Okay? So, we have 2 atmospheres, 1 atmosphere, 6 atmospheres, based upon the number of molecules that are in there at the same temperature, same size container. Okay? But now we're going to mix them all and put them into here. Well, there's the answer. So, I have my 2 atmospheres here.
Oh,
Hey.
I got my 2 atmospheres here. I have my 1 atmosphere here, and I have my 6 atmospheres here. So, if this went into a 1-liter container, what's my pressure going to be if I put them all into a 1-liter container? 9, right? Because of whose law?
Oil.
Dalton's law of partial pressures.
Dalton's law of partial pressures. I just already come, I can't distinguish here. Dalton's law of partial pressures. The total pressure is the sum of the individual pressures. So even though we're mixing them all into the same container, they're going to act like it's there, it's not there. They're all just still going to be there. But we're in a 2-liter container. So if we have 9 atmospheres, but now it's in 2 liters, what's going to happen to the pressure? It's going to be half, right? So it's going to be the 9 atmospheres divided by 2, which are 4.5 atmospheres. Now, a completely different way to do it would be 2 atmospheres from 1 liter to 2 liter. What's the pressure of this gas in the new container?
1 atmosphere.
It's going to be 1 atmosphere. What's the pressure of this neon going to be in the new container? 0.5. And this one's going to be 3 atmospheres. So now my total pressure, again, 4.5 atmospheres. Dalton's law of partial pressure. Okay? Now, hold that thought. And let's finish this problem. It says, gotta go back, I think. No, it was on there.
I thought it was on the paper.
No, I have it pulled up in the classroom.
Yeah, that's right, yeah.
Yeah. Okay. So, we know also that the total pressure of this problem is given as 4.69 atmospheres. So what do I do from here?
4.69/3 would be N2O4, and then 4.69 times 2/3 would be for NO2.
Well, that's if they were equal amounts. But equilibrium doesn't mean equal amounts. Okay? What's making up this pressure though? You're on the right track.
Those
Other
two.
than those gases.
It's going to be the pressure of the N2O4 plus the pressure of the NO2. Okay? So, I can't have two variables in an equation. Somehow or other I have to, get down to one variable so I can solve for my unknown. Now, I know that initially, what's the pressure inside, before any decomposition occurs, what do we find the pressure to be?
2.9.
2.93 atmospheres. There was 0 of this because they only put that in. But some of it, but not all of it, only some. Remember we just said equilibrium means there's always going to be some of each thing. So, using those ratios, we don't know how much, but how can we represent this then with a variable? Do we know how much it's going to decompose?
Yeah.
We can just say minus x. But if I say minus x here, how much of this is going to get made? If x amount reacts, how much of that's going to get made?
2x.
2x. Because for every 1 you get 2. So this is going to be plus 2x. So at equilibrium, okay, at equilibrium we're going to have 2.93 minus x and 2x of this. Now I have a relationship with one variable between the two gases. So I can say now that it's going to be 2.93 minus x plus 2x. Now one of the x's are going to cancel out, so it's going to be plus x. So you subtract the 2.93, and you're going to get 1.76 atmospheres is equal to x. Now does x equal anything? What's the question asked?
Find the partial pressures.
Okay, is x the partial pressure of any of the gases?
No,
How do I find the partial pressure of this one?
plug it in.
2.93 minus 1.76 is equal to 1.17 atmospheres, whereas this one is going to be 2 times 1.76, which is going to equal 3.52 atmospheres. Okay? So it's Dalton's law of partial pressure. You're going to know you have to do this when you're given the total pressure. Right? When you're given the total pressure. Did anybody get this one right? Did the 3 over 2, did your 2/3 work?
Oh, I can check if it would. I raised it, but I can check.
Oh. There's always more than one way. It is just all about the mole ratio. But I don't know if you started with the 2.9.
No, I forgot to account for that.
Yeah. Yeah.
It was slightly off. I
Okay.
got 0.4.
All right, let's go back to that exam. All right, now let's go to the next page. Next page. Okay, this is the one I really want to look at. Because this one is similar to this one. All right. So again, I want you to see how AP is going to ask these questions. So we have PCl5. decomposing again into PCl3. Lousy, that's a lousy thing. Okay? Now we're starting with 1 atmosphere. 0 and 0. So let's look at the first question, number 29. So scroll down, number 29. Okay, which of the following is most likely the cause for the increase in pressure? Because now I know that my total pressure is equal to 1.40 atmospheres. And it's saying it's the result of the pressure of the PCl5 plus the pressure of the PCl3 plus the pressure of the Cl2. Everything that's present is adding together to make this. But why did the pressure go up? Look at your answers and pick one without saying it out. Does anybody think it's A? Does anybody think it's B? Does anybody think it's C?
Okay, good.
That was a casual turnaround. That's funny. Okay, that is the correct answer, okay? An increased number of molecules because 1 is breaking up into 2. So now we have more molecules present. This number goes down, but this is going up by, for every 1, by 2. So you know you're going to have more molecules in the final than you do in the initial. Okay? Now let's go back up to 30. As the reaction progresses towards equilibrium, the rate of the forward reaction, what do we know about equilibrium? What happens?
The rates are the same.
So the rate's going to, it's going to start off fast. Now this is going to be more of a kinetics type and equilibrium type question, but we'll just touch on it. It's going to start off, but what's going to happen to this concentration over time? Is it going to go up or go down?
Down.
So what do you think about the rate of the reaction? Faster or slower? Slower. The fewer molecules you have, the less they're going to collide, the less is going to happen. The reaction is going to slow down. Until the forward rate and the reverse rate equal one another. So it's going to start off fast, you have none of this, then it's going to slow down, and this one's going to begin, this is getting more and more concentrated, so this one's speeding up, until finally they're equal. Now a lot of students miss this one. They got the decreases, but they put to become 0. Well, that would mean that it stopped going this way completely. But we know that at equilibrium it's constantly going back both. So it decreases to some non-zero rate. Okay, the forward rate doesn't stop completely. It just slows down to where the forward and the reverse equal. Okay? That's just a bonus in there. That's just a foreshadowing which to come. 31. Great question. You read it and answer it without, just in your head.
In our head.
So you read it, but I just don't want you to say an answer out. Okay, you should be finished by now. What'd you get, Hampton? B. 2, that is correct. Why did you choose B?
Because the number of molecules doubles, and so.
So if it goes to completion, that means that all of this goes to here.
Yeah.
So you're going to have twice the molecules, twice the pressure. Okay? Now, we get to 32 on the next page, which is the one I really wanted to look at. All right, now I'm going to tell you this. We're going to learn about Kp. But Kp is going to equal the pressure of the PCl3 times the pressure of the Cl2 divided by the pressure of the PCl5. Okay? You'll learn this in February. Okay? But knowing this, what we need then are the partial pressures of the three gases, which we know how to do now. So how do we do this one now? How do I find the pressure of each one of those?
Well,
Go ahead, Isma.
maybe you could do it like compared to PCl5, because like if you know that one's bigger and it's one of the top two, I think would be less than one, because that one just asks.
Okay, but let's do it mathematically.
Oh.
How did we do the last one?
So
This is where I was initially.
PCl5 might could be 1 ATM minus 2x,
2x?
Just
or just x.
There's just a 1 there, so it's going to be minus x.
and then the other two would be x too.
Be plus x and plus x, correct?
Yes.
So initial change, so at equilibrium, this is going to be 1 minus x, x, and x. Right? So how do I use that?
And you do that equal to 1.40.
So now we just kind of plug in the values into here using Dalton's law, because again it says the total pressure was 1.4. That's my clue that I'm going to have to use Dalton's law to find out what the pressures are of each individual one. So it's going to be 1 minus x, plus x, which makes the math easy, okay? Because then x, because one of the x's cancel out. So 1 plus x is equal to 1.4, so it's just subtract x equals 0.4. Okay? Now the question's asking, is this going to be greater than or less than 1? Well, x and x are both 0.4 times 0.4. What's PCl5 going to be? 0.6. Now, you don't have a calculator. Multiple choice, you don't get a calculator. But what's 4 times 4?
16.
So 0.4 times 0.4 is
0.16.
0.16 divided by 0.6. Is that greater than or less than 1? Less than 1. That's all you have to do. You don't have to be able to do the actual math. You should know that 0.16 is less than 0.6. Okay? You are expected to be able to do 4 times 4. I know it's asking a lot. I haven't done the multiplication tables like I normally do throughout the year to get you all refreshed on them, but we'll come back on that. All right, let's go down all the way now. Let's just keep going. Next page. Next page. I don't see anything here. Next page. Next page. Let's go all the way to like 57. Keep going. Go one more. Yeah, number 60. Okay. Now, I'll tell you on this one, and I'm going to let you guys do this. But now we have CO, Cl2 decomposing to CO plus Cl2. Okay? And again, it starts off at what, 1 atmosphere?
Yeah.
Well, I say there it is, 1 atmosphere, so my initial. And by the way, y'all, these are called ice tables, what I'm kind of doing, and we're going to do a lot of these in equilibrium. Initial change equilibrium. Ice, ice, baby. Okay? Now I also know that my total pressure, 1.2 atmospheres. And what I'm going to tell you is that Kp is going to equal the pressure of the CO times the pressure of the Cl2 divided by the pressure of the CO Cl2. So knowing this, figure out the answer to number 6.
Mr. Hobbs.
Yeah,
Oh,
I know.
okay.
I'm doing that on purpose.
Oh, okay.
I'm looking for something.
I was like so confused where my phone was, and I realized I put it in my lunchbox.
Y'all, there's me and my new bride. This is, okay, funny story though?
Yeah.
I can't say this on video. Probably shouldn't watch.
You could turn off the video, I mean.
Yeah.
Edit it out.
So we're all there, okay, we're at the church, because it's small, it's just family and a couple of friends, okay? 25 people at the most. So, her son and my son played a song to start the ceremony. My son played, he sang. And then they finished, my son went to the piano, he went to the back, started walking her down the aisle. Okay, she gets down to me. We do the first little bit just on the floor, and then we're supposed to walk up the stairs, get on the actual stage. She turns to me and says, "I forgot the ring." But I'm the only one that heard that. And so she says, "I'll be right back," and takes off back out of the church. And my friend who's there says, "Abba, you just got left at the altar." And so she was embarrassed, but she came back, you know, so then we went on with the rest of the ceremony, but she feels horrible about that. Just scroll to the next other 2 pictures, just hit the right arrow and it should
Yeah.
go. And then up, and then down at the bottom,
There you go. There's that one.
yeah, and then one more,
And I'd like go back to the image.
yeah. Anyway,
That's that one.
Aw,
a happy couple.
There's
I
that
now have a wedding ring on. So,
that's cool.
one.
all right, so now we'll go back to the problem. We finished with the problem?
No.
Is it,
I couldn't see
There
it.
it is.
Okay.
what do a 1, 2, 3, and 4 for A, B, C, D, what did you get as your answer? Just hold up the finger. Don't spoil it there. Okay, what'd you get, Ethan?
Or what?
Okay, just give me a finger, 1, 2, 3, or 4 for A, B, C, or D. Okay,
What's that, Nathan?
waiting on you.
I think I got it. This second.
Okay, that's all, y'all did right. Okay, so what's this gonna be?
1.0, wait, minus x
Minus x
plus x.
plus x plus x. Now, if this was a 2, what would that be?
And 2x.
2x. Okay, but it's always whatever the coefficient is. So we're gonna have 1 minus x, x, and x, so what do I do with that?
You make them all add up to 1.20.
Okay, so it's gonna be 1 minus x plus x plus x, so these two cancel out. So it's 1 plus x, so subtract, so x is equal to 0.2. Okay, so that makes this 0.2, that makes this 0.2, what does it make this one?
0.8.
0.8. Now, this time we want the actual answer, so it's gonna be 0.2 times 0.2 divided by 0.8. Now, tough math again, 2 times 2 equals,
4.
therefore this is 0.2 times 0.2 is
0.04.
0.04. 4 divided by 8 is
1/2.
0.5, so 0.04 divided by 0.8
0.05.
0.05. Now, but you know 4 divided by 8 has to be 0.5 somehow, so this is the only one that is the 5, so even if you get your decimals messed up, okay, you know it's gotta be that one.
Yeah, that's what I was doing. I was like, you know, whatever. It has a 5.
That's exactly right, and so don't stress over that, you know it's gotta be the point, it's gotta be a point either 5, 0.05, 0.005, it's gotta be the 5. Alright, so the key on this, total pressure, you know you have to use Dalton's law. That means I have to have an ice table. Whenever you have equilibrium and some reacts, you're gonna wanna set up something like this. When it all reacts, we just do normal stoichiometry. But when only some reacts, we have to just kinda use X. You with me on that? Alright. Now, I assigned some practice problems for you to work on tomorrow and Wednesday and Friday. Due at midnight. This is one of them. It's on a separate sheet. It's actually typed up on the sheet, but this is basically going to do one for you on.
Thank you.
Thank you.
Okay. So it says, and I want to bring this down. I want to write on the board. So I have 3 mole sample of this, and I have a 10 mole sample of this. Are placed into a previously evacuated vessel. What does that mean and why?
It's a vacuum.
Okay, so what's the significance of saying that?
There's nothing else in there except for that.
Nothing else in there except for this. That's all that means. So don't let that stress you out. Where they meet to react according to the equation above. After one of the reactants has been totally consumed, how many moles of C2H2F4 have been produced? Okay? So how did you know that, Isla?
It's still limiting reactant.
How do you know it's the limiting reactant, Hampton?
Because it has the least amount. You divide the 10 moles.
10 divided by 2
Is 5.
is 5. This divided by 1. So this is going to be my limiting reactant. So since it's 1 to 1, 3 moles is going to produce
3 moles.
3 moles. But what if I said I had 3 atmospheres and 10 atmospheres I wanna know what the new pressure of that, the partial pressure of that's gonna be.
So would that be like total pressure or part?
Now, partial pressure of the C2H2F4.
8,
Oh.
13.
What determines pressure?
Number of moles.
The number of moles.
Oh.
If it goes to completion, how much of this is
So
left?
it would be a 3.
None.
None.
It would be 3
It's gonna be 3.
because it has the same amount as the C2H2.
3 moles made 3 moles, therefore 3 atmospheres will produce 3 atmospheres. And the same number of molecules equals the same pressure. Okay? So it's gonna equal 3 atmospheres. Now, what would the total pressure be?
13.
No.
No.
Some of the F2s.
Oh, it would be, that's right.
So,
7.
yes, how'd you get that?
Because if you use 3 moles of C2H2, you would need, well, because it's 2, you would have to use 6 of that.
Okay?
So that would be 4. So 3 plus 4 is 7.
So the pressure of the pressure of the F2 plus the pressure of the C2H2F4 is going to equal 4 atmospheres. Does everybody understand where 4 atmospheres comes from? You started with 10, but 6 got used. 3 times 2, 6 got used, so you have 4 atmospheres excess. Plus the 3 atmospheres that got made. So the total pressure in the flask is going to be 7. It's not going to be 13 because this disappears. These all go away to produce this. Okay? Lastly, what if I said 3 liters combined with 10 liters? How many liters of C2H2F4 am I going to get? There's a trend here, let me just tell you that.
3.
3. Okay. Now, why? Anybody recall Avogadro's principle?
If
You
the
remember.
pressure, temperature, and volume are the same, the number of moles are the same.
Gases at the same conditions of temperature and pressure. They're all, inside here. Equal volumes are going to contain the same number of molecules. Okay? So volume and molecules of a gas are proportional, directly proportional. So if I have 3 liters of a gas and I have another gas that's going to react with it, I'm going to need 6 liters of this gas that have twice as many molecules of fluorine as I do acetylene. Okay? So it's a 2-to-1 ratio. So the volumes combine in the same ratio here. So you'd have the equivalent of 4 liters of the fluorine left unreacted. Okay? So what's the takeaway from all this?
Everything is 3.
Everything is 3. 3. The answer is always 3. No. What point am I trying to drive home here?
It's all connected.
It is all connected. Oh, my finger almost wasn't getting caught up there. I'm not used to having that. What are we relating here? What's all 3?
Moles, atmospheres, and liters.
Moles, atmospheres, pressure, liters, and volume. What does that mean about their proportionality?
Direct.
They're all proportional, they're all directly proportional. So you can do gas law stoichiometry problems in terms of moles, in terms of volume, or in terms of atmospheres, pressure, and you're always going to be in the same ratio as the coefficients of the balanced equation. Because the pressure is related directly to how many moles are present. The volume is related directly to how many moles are present. Equal volumes contain the same number of moles. Pressure is caused by collisions with the container walls. Equal moles equal collisions. So we can do this. It doesn't matter in these problems whether it's given in moles, it's given in atmospheres, it's given in liters. You always use the coefficients of the balanced equation, as long as everything's at the same conditions, which this is all in the same container, so it's under the same conditions. That is an extremely important concept. Okay? Extremely important concept. We good with all that? So tomorrow, you're going to get to work on some more of these practice problems. Okay? Now, you won't have to get them all